Hello and welcome back to the Deep Dive. We are absolutely thrilled to be back with you for the third installment of our specialized series, the EMI Control Podcast.
It is good to be back.
If you've been with us for the first two, you know we've been building up to this.
I think so, yeah. And frankly, today is the big one. We are tackling a subject that I think keeps more electrical engineers awake at night than almost anything else in the hardware world.
The invisible enemy.
The invisible enemy.
The thing that just ruins your week right when you thought the product was done.
Exactly.
And before we dive into the deep end here, we have to give credit where it's due.
Absolutely.
This entire series and the incredibly deep insights we're unpacking today, they're all provided by Frisu Electronics.
Right.
Specifically, we're drawing directly from the expertise of Dario Frisu.
And that's a name that carries a tremendous amount of weight in this field. Dario is the CEO, the principal engineer, and a dedicated EMI specialist.
So this isn't just theory.
Not at all. The material we're working with today isn't just textbook stuff. It is field-tested, battle-hardened, practical knowledge.
This is coming from someone who solves these problems for a living.
That's the key.
Which is exactly what we need because, let's be honest, the topic today is radiated emissions. And I feel like in the engineering world, electromagnetic compatibility, or EMC, it has a bit of a reputation.
You mean the reputation of being black magic?
Exactly.
Okay.
The black magic of engineering. It feels like you design a board, it works perfectly on the bench, your logic is sound, your code is clean.
Everything's perfect.
Then you take it to the compliance lab, you stick it in that chamber, spin it around on a turntable, and suddenly it's failing.
The graph is red.
The graph is red, and nobody knows why. It feels like you need a wizard, not an engineer, to fix it.
That is the common fear, isn't it? It feels completely unpredictable.
Yeah.
But the mission of this deep dive, and really the core message from Dario Frisu and his team, is to completely dispel that myth. We are here to say, very firmly, it is not magic.
It's
What? It's
physics. I love that.
Yeah.
So we're trading wands for equations today. No more casting spells, just applying laws.
Precisely. It is a disciplined science based on established principles. It operates on the same laws of physics that make your toaster work or, your car drive.
And the stakes couldn't be higher.
Oh, absolutely not. If you treat it like magic and just kind of hope for the best, you are gambling. You risk failing FCC or CE standards.
Now, we all know what that means. It's not just a bad grade on a test.
No, it is market delays. It's redesign costs that can run into the tens or, hundreds of thousands of dollars.
It's wasted resources, missed shipping dates.
It's a nightmare scenario for a business, but if you treat it like physics...
You can control it.
You can control it. You can predict it.
So let's get into the physics then. Where do we even start? Because when I think of electronics and when I think of signals, I usually think about voltage.
Right.
Is that where the problem begins? Is it high voltage that creates these emissions?
And that is actually the first trap. This is the core concept we need to nail down right at the start.
Okay.
Radiated emissions are not driven by voltage, they are driven by current.
Okay, let's unpack this. Because usually we worry about voltage spikes or signal levels, voltage drops.
All the time.
But you're saying for EMI, for the radio waves literally leaving the board, it's the flow.
It is all about the flow, specifically time-varying currents.
Time varying.
A static current, DC, doesn't radiate much. You could have a huge DC current, and it's relatively quiet in terms of radio frequency emissions.
Okay.
But as soon as that current changes, which is what happens in every digital signal, right? Switching on and off, going from 0 to 1 and back.
Yeah, you generate electromagnetic fields.
You've got it.
Maxwell's equations, right? A changing electric field creates a magnetic field.
And a changing magnetic field creates an electric field. They propagate. They become a wave.
So the source material puts it really well, right? It says we can't stop currents from radiating entirely.
It's physically impossible. As long as you have a changing current, you have radiation. It's like built into the fabric of the universe.
So we're fighting a losing battle. If we can't stop it, why are we even here?
It's not a losing battle, but it is a management battle.
Okay.
The shift in perspective is this. We can't stop the radiation from existing, but we can manage how efficient that current is at radiating.
Ah. So we want to make our circuits terrible antennas.
I love that phrasing. We want to be the worst antenna designers in the world.
We want our board to be mute.
Exactly. We want it to keep its energy to itself.
Okay, so if current is the bad guy here, or at least the source of the noise,
Right.
we have to ask, are all currents created equal? Or are there different types of current crimes we need to look out for?
I assume there's a distinction, otherwise this would be a very short deep dive.
Yeah.
There are absolutely distinct types. And this brings us to part 1 of our discussion. The two culprits.
The two culprits.
In the world of EMI, strictly speaking regarding radiation, we divide currents into 2 categories: differential mode and common mode.
Differential versus common. Okay, let's break those down.
Yeah.
Differential mode sounds correct. Like, that's the difference in potential we want.
You're exactly on the right track. You could call it the intended traffic.
The intended traffic.
Differential mode, or DM, is the current that drives your operation. It's the signal leaving the source, say your microcontroller output pin, going down the trace to the load, maybe an LED or memory chip, and then, crucially, coming back on the return path to the source.
Right. Signal goes out, return comes back. That's electronics 101. It's a circuit. It has to circle back.
And that's the good stuff. That's the data.
Correct. That is a functional current.
So what is the common mode then?
Common mode, or CM, is the parasitic stuff.
Parasitic.
It's the ghost traffic.
Okay.
These are unintended currents.
Okay.
Instead of going out on one line and back on another, common mode currents flow in the same direction on multiple conductors simultaneously.
Wait. So they're both heading the same way, like on the signal wire and the return wire, they're both flowing out.
Yes. Imagine 2 cars on a 2-lane highway. Differential mode is normal. One car goes north, one car goes south.
Okay, makes sense.
Common mode is both cars going north, side by side.
But if they are both going out, where is the return? A circuit has to close, right? Physics demands a loop.
That is the scary part.
Yeah.
And that is why it is so hard to manage.
Where does it go?
Common mode currents usually find a return path through the chassis or through the earth ground.
Or
through stray capacitance coupling to the environment.
Stray capacitance. You mean it's jumping through the air?
Effectively, yes. It couples to the metal frame of your desk or the floor or the nearby equipment just to get back to the source.
So it's not a path you designed on your schematic?
No, it's a path the physics found for itself.
That sounds incredibly difficult to diagnose.
It is.
If I'm in the lab staring at a failing spectrum analyzer, just seeing a big spike at 100 megahertz, how on earth do I know if I'm looking at differential mode noise from my traces or this ghost common mode noise from who knows where?
This is where we get our first real aha moment from the Fraser Electronics guy.
Okay.
There is a diagnostic trick, a physical experiment you could do right on the bench without any fancy software.
Oh, I love a good bench hack. Practical tips are the best. What is it?
It's surprisingly simple. You just take the cables or conductors leading away from your board, and you move them closer together. You physically squish them.
That's it. Just group the cables.
Effectively, yes. But here is the physics behind why that works.
Okay.
It tells you immediately what you're dealing with. If the emissions on your analyzer drop when you move the cables closer, you are dealing with differential mode.
Why? Why does proximity help differential mode?
Because remember our highway analogy.
Opposite directions.
Differential mode currents flow in opposite directions. One goes out, one comes back. According to electromagnetics, current flowing one way creates a magnetic field spinning clockwise.
Right.
Current flowing the other way creates a field spinning counterclockwise.
Okay, opposite fields.
And opposite fields want to cancel each other out.
Oh.
By bringing the conductors closer, you are tightening the coupling between those 2 wires. You are helping those opposing fields overlap and neutralize each other.
Makes sense. Tighter coupling, better cancellation. The fields fight each other and poof, they disappear.
Exactly. But imagine you move the cables closer and the emissions stay exactly the same.
The spike doesn't budge.
The spike on the screen doesn't budge. That is common mode.
Because they're flowing in the same direction.
Correct. If both currents are flowing north, both magnetic fields are spinning the same way.
There's no cancellation.
There's no cancellation happening between those 2 wires. They are reinforcing each other.
Right.
So their proximity to each other is completely irrelevant to the radiation magnitude.
That is such a useful heuristic. It's like a binary search for the problem.
It is.
If squeezing the cables fixes it, it's differential. If it does nothing, you're hunting a ghost.
Precisely. And knowing which enemy you are fighting tells you which weapon to use.
Right.
You don't treat a virus with antibiotics, and you don't treat common mode with differential mode fixes.
Okay, so let's take a deep dive into that first enemy, differential mode.
The intended current. The one we actually need to make the board work.
So you mentioned it flows in a loop, out and back.
Yes. And in the world of physics, a loop of current is literally a magnetic component.
Okay.
It acts as a small loop antenna. When we say small, technically we mean the circumference is smaller than a quarter of the wavelength of the signal.
Yeah.
But for our purposes, just visualize a loop.
Okay, I'm picturing a loop, like a lasso on the circuit board.
Now imagine the radiation coming off that lasso. It forms a specific shape. It's not a sphere.
No.
It's a donut or toroidal shape.
Like a donut. Okay.
And the strongest signal radiates out in the plane of the loop, so the edges of the donut.
So if my board is flat on the table and the loop is flat on the board, the radiation is shooting out sideways.
Predominantly, yes.
Yeah.
Toward the other equipment.
Right.
There are nulls, quiet spots pointing straight up and straight down. But the loud part is shooting out horizontally.
Now, we have a formula for this, and I know hearing formulas on a podcast can be tough.
Yeah, audio formulas are hard.
But we're going to break it down conceptually because it tells us exactly how to fix the problem.
Let's do it. Break down the variables. What makes this signal louder?
The formula calculates the electric field, we'll call it APOL. That's what the compliance guy measures with his antenna.
Okay.
There are 3 main levers that make it'll go up. The first, and honestly the most terrifying one, is frequency. Little dollars.
Why is frequency terrifying? Usually faster is better, right?
For performance, yes. For EMI, no. In the radiation formula, the emissions relate to the square of the frequency. Russell.
The square. So if I double my clock speed,
You don't double your emissions.
I quadruple.
You quadruple them. If you go from 100 millihertz to 1 gigahertz, that's a factor of 10.
Your emissions go up by a factor of 100.
A factor of 100.
Wow. Okay, that explains why modern electronics are so much harder to certify than stuff from the 80s.
Exactly. We are climbing an exponential curve of difficulty.
Okay, so speed kills. What's the next variable?
Current. Dollar. This one's linear.
Okay.
More current equals more radiation. If you drive a heavier load, you get more noise. Simple enough.
And the third?
Area. Big dollar. The physical area of that loop we talked about. The geometric space between the out path and the back path.
So we have frequency squared, current, and loop area. This sounds like an engineering dilemma,
It is.
because I can't really change the first two, can I?
That is the classic dilemma. Think about it. Can you usually change the frequency?
Probably not. The system spec says we need to process video at 4K.
Right.
And that requires a certain clock speed. If I slow it down to pass EMI, the product doesn't work.
Exactly. You can't just underclock the device. What about current? Can you change that?
Maybe a little. But usually the chip needs a certain amount of power to drive the line. The physics of the silicon dictates the current.
Right. You are constrained by the functionality of the device. So if you can't touch frequency and you can't touch current, what is left?
The loop area.
The loop area. This is the designer's primary lever. This is where the battle is won or lost during the layout phase.
You have total control over the geometry.
Total control.
So practically speaking, how do we minimize this area? I assume we're talking about PCB layout here.
We are.
We need to squish the loop.
And the most critical factor is the stack up, the arrangement of copper layers and insulation in your board.
The stack up. Okay.
Imagine a simple 2-layer board. You have a signal trace on the top layer. Where is the return path?
Well, if it's a messy board, maybe it has to wander all over the place to find a ground pin.
And that wandering creates a massive loop area. Imagine the signal goes 3 inches north, and the return path has to go 3 inches east, then south, then west to get back.
The area inside that is huge.
It's a massive antenna.
So how do we fix it?
You use a multi-layer board, and you design a stack-up where the signal layer is immediately adjacent to a solid return reference plane, or RRP.
We usually just call that the ground plane.
Yes, but return reference plane reminds us what it's for. It's the return path.
Okay.
If you put a solid plane right under the signal trace, the physics of inductance will force the return current to run directly underneath the signal trace.
Like a shadow.
Exactly, like a magnetic shadow. It hugs the signal trace perfectly. So the physical gap between the signal on layer 1 and the return on layer 2 is just the thickness of that dielectric material.
Which is tiny. Maybe 4 or 5 mils?
It is microscopic, so your loop area isn't square inches anymore. It's square millimeters or less.
And since emissions are directly proportional to that area.
A microscopic loop means microscopic emissions.
It's amazing how geometry dictates success here. It's not about adding expensive filters yet. It's just about where you put the copper.
Geography is destiny in PCB design. A good stack-up solves 80% of your differential mode problems before you even place a component.
I want to circle back to frequency for a second. You said it scales with the square of the frequency.
Right.
But digital signals are weird, aren't they? They aren't sine waves. They're pulses.
That is a very important technical nuance. We tend to think of a 100 megahertz clock is just 100 megahertz. But a digital square wave is composed of a fundamental frequency plus an infinite series of odd harmonics.
The Fourier series, I remember that from college.
Exactly. 300 megahertz, 500 megahertz, 700 megahertz, and so on.
Okay.
Now, in the real world, signals aren't perfect squares with vertical walls. They are trapezoids. It takes a non-zero amount of time to rise from 0 volts to 3.3 volts.
The rise time.
The rise time. And this is critical. The faster the rise time, the steeper that slope, the more energy is pushed into those higher harmonics.
So even if my clock is slow, if the edge is super sharp?
You have a high-frequency problem. You might have a 10 millihertz clock, but if it switches in 1 nanosecond, you are generating noise up into the gigahertz range.
And we look at this on a graph, right? A Bode plot.
Yes. If you plot the emissions frequency spectrum, you see these breakpoints.
Mm-hmm.
The emissions rise fast, 40 dB per decade, up to the first breakpoint, which is related to the clock frequency, but then there's a second breakpoint.
And that one is determined by the rise time.
Precisely. This second breakpoint often hits around 200 megahertz or higher. Above that frequency, the emissions roll off.
No.
If you slow down your edges, make the trapezoid a bit more sloped, you bring that breakpoint down in frequency. You filter out the high-frequency junk.
So the takeaway there is, don't use a faster rise time than you actually need.
Exactly. If you don't need a Ferrari engine to go to a grocery store, don't use one.
Right.
If your protocol works with a 5 nanosecond rise time, don't use a driver that does it in 500 picoseconds. You're just creating noise for no reason.
All right, so that's differential mode. Control the loop area using the stack up and watch your rise times.
In a nutshell, yes.
Now, let's pivot to the other culprit, the one you call the silent killer.
Ah, yes. Common mode.
Common mode.
CM is indeed the silent killer. And the reason it's silent, at least during the design phase, is because it's not on the schematic.
You can't see it.
You can't point to a trace and say, that's the common mode trace. It's the current that isn't supposed to be there.
It's just leakage.
It comes from parasitic effects, stray capacitance, inductance, impedance, mismatches. It's the leakage.
And you mentioned earlier that these currents flow in the same direction. Why is that worse? We talked about cancellation for differential mode.
It comes back to the antenna. In differential mode, the fields cancel out because they are opposite.
Right.
In common mode, the currents are flowing in parallel, same direction. The fields create what we call constructive interference.
Like stack.
They add up. They maximize their ability to radiate. And to make matters worse, the antenna for common mode isn't a tiny loop on the board. It's usually the cables attached to the board.
The USB cable, the power cord.
The Ethernet cable, or the whole metal chassis itself.
So instead of a millimeter-sized antenna, I have a meter-long antenna.
Exactly. And a meter-long antenna is a very, very efficient radiator for the frequencies we care about, like 100 millihertz to 1 gigahertz.
Okay, I want to quantify this. Is it twice as bad? 10 times as bad?
Here is a stat from the source material that genuinely shocked me.
Okay.
We can compare the radiation potential mathematically using the standard formulas. There's a constant in the radiation formula for both.
Let's hear the numbers.
For differential mode, the constant involved is roughly 10 to the minus 16.
Okay, that's a decimal point, 15 zeros, and a 1. Tiny.
Vanishingly small. For common mode, the constant is roughly 10 to the minus 7.
Whoa, wait. 10 to the minus 16 versus 10 to the minus 7? That's 9 orders of magnitude.
Depending on how you factor in the length and current, practically speaking, common mode is about 1,000,000 times more efficient at radiating than differential mode.
1,000,000 times.
1,000,000.
That is absolutely wild. So you're telling me I can have a massive differential current, and it might be fine.
Right.
But a tiny trickle of common mode current.
A few microamps, just a whisper of current.
Wow.
A few microamps of common mode current on a cable can cause a compliance failure that would require amps, literally whole amps of differential mode current to replicate.
That puts everything in perspective. You can have a perfectly designed differential signal, your loops are tight, your stack up is great.
All of it.
But if a tiny ghost current leaks onto the cable, you're done.
You are done. That is why we call it the silent killer. It takes almost nothing to fail a test.
That's like a drop of red dye in a swimming pool.
It is. It's very hard to get out once it's there.
So how do we fight it? If it's invisible, highly efficient, and uses our cables against us, are we helpless?
Not at all. We have 3 main strategies. First, shorten the antenna.
You mean cut the cables? The user might not like a 3-inch power cord.
Well, reduce cable lengths if you can, but also look at the antenna structures on the board.
Uh-huh.
For example, if you have a crystal oscillator, a very noisy component, place it right next to the pins of the chip it's driving.
Don't let that clock trace wander across the board.
Exactly. If you run a long clock trace, that trace itself can become part of the antenna structure that couples to the environment. Keep high-frequency sources tight and contained.
Okay, keep it compact. What else?
Second, filtering. This is where components like common mode chokes come in.
A choke. It sounds aggressive, like we're strangling the noise.
That's effectively what it does. A common mode choke is a magnetic component that acts like a gatekeeper.
Okay.
Because of how it's wound, it allows the differential signal, the data you want, to pass through freely.
Ow.
The magnetic fields inside the core cancel out for the differential signal. So the data doesn't even see the choke.
Ideally, no.
But for the common mode current, which flows the same way on both wires, the choke presents a massive impedance.
It looks like a brick wall.
It chokes the ghost current and stops it from getting onto the cable.
And the third strategy.
Shielding. If you can't stop the radiation at the source and you can't filter it all out, you contain it.
Right.
You use shielded cables, like a coaxial cable or a shielded USB, to wrap the field in metal and keep it inside.
But shielding is tricky, right? I feel like I've seen people mess up shielding a lot.
They do.
It seems like if you don't ground the shield right, it makes things worse.
A bad shield can be worse than no shield because it acts like an even bigger antenna.
Wow.
And that actually leads us into part 4 of our discussion, which is the role of the return path.
Okay.
Because often common mode currents are created because the return path is bad.
This goes back to the ground is not a trash can concept.
Yeah.
We treat ground like a magic drain, but it's actually a wire.
Exactly. We need to stop calling it ground and start calling it the return reference plane. The goal here is low impedance.
Low impedance is king. Why?
Because of Ohm's law. It always comes back to Ohm's law. Voltage equals current times impedance. $V explains I times Z.
Okay.
If your return path, your ground plane, has high impedance, when the return current flows through it, it creates a voltage drop across the plane.
So the ground at one side of the board is at a different voltage than the ground at the other side.
Precisely. We call that ground bounce or ground noise.
Right.
That voltage drop essentially lifts the potential of the ground relative to the earth or the chassis. And that voltage potential is what drives the common mode current out onto the cables.
It pushes the current out.
It's a pump. We want the return path to be slippery. We want the current to slide back to the source with zero resistance, creating zero voltage drop.
So how do we make it slippery? How do we minimize that impedance?
The solid plane rule. This is non-negotiable for high-speed design.
What's the rule?
Never, ever cut or split your return reference.
But what if I have a lot of traces on the signal layer, and I just need to make a little slice in the ground plane to route one more wire?
Be very careful.
Or maybe I want to separate analog ground from digital ground.
That's a whole other topic, but be very, very careful. The source material gives a great comparison here.
Okay.
A solid, uninterrupted plane has an inductance of about 0.15 nanohenries. It is extremely slippery for high-frequency current.
Okay, 0.15, very low.
Now imagine you cut that plane and force the current to flow through a narrow bridge or a trace to get across. The inductance jumps to about 15 nanohenries.
A factor of 100.
2 orders of magnitude. If you force the return current to go through a thin strip of copper, because you cut the plane, you just increase the impedance by 100x.
You just created a massive voltage drop.
You basically built a common mode generator.
Okay, so the rule is simple. Don't turn your ground plane into Swiss cheese. Keep it solid.
Keep it solid.
But we have multi-layer boards, signals, jump layers. They go from top to bottom.
Yeah.
What happens to the return current then?
This is a critical visualization. Imagine the signal current is running on the top layer, and the return is running underneath it on layer 2, the ground plane.
Right, the shadow.
Now the signal goes down a via to layer 3. The signal takes the elevator down.
But the return current is stuck on layer 2. It can't go down the signal via.
Exactly. And physics requires the return current to follow the signal to minimize the loop area.
Right.
If you don't give it a path, it has to wander around layer 2 looking for the nearest ground via to get to the next reference plane.
And that wandering creates a loop.
The loop area explodes again. You broke the stack-up rule we talked about earlier.
So how do we fix it? We need a ground elevator.
Exactly. The fix is stitching vias, or return reference vias, RRVs. You place a ground via right next to the signal via.
So you're building an elevator for the return current right next to the elevator for the signal.
That is a perfect analogy. You allow the return current to jump layers immediately adjacent to the signal current. You keep the loop tight, even in the vertical dimension.
I love that. It's all about maintaining that geometry in 3D space.
It is.
So we've covered the board design, but earlier you mentioned shielding mistakes. I want to get to part 5, the practical mistakes, because I've heard about something called the pigtail sin.
The pigtail sin. Oh, yes. It is the bane of every EMC engineer's existence. It is the most common reason for shielded cable failure.
Describe it for us. What is a pigtail?
Okay, imagine you have a nice, high-quality shielded cable. Maybe it's a thick industrial cable. It has a beautiful metal braid wrapping all the wires inside to keep the noise in.
Got it.
You get to the connector, and you need to connect that shield to the chassis or the board ground.
Right, you have to ground the shield.
So the technician peels back the jacket. He unbraids the end of the shield, gathers all those little wire strands, and twists them into a single wire.
Which looks like a pig's tail.
And then he solders that single twisted wire to a ground pad on the board.
It looks neat, though. It keeps things organized. Why is it a sin?
Because you just committed a crime against physics. You took a low impedance, 360-degree shield, which is like a wide pipe for current.
Right.
And you funneled all that current through a thin, high-impedance wire. You created an inductor.
You bottlenecked it.
You bottlenecked it completely. At DC, it conducts fine. But at high frequencies, 100 megahertz, 500 megahertz, that pigtail has significant impedance.
Ohm's law again.
Yes. The noise current hits that pigtail, sees high impedance, and says, I can't go to ground this way, so instead it flows over the outside of the shield and radiates.
So the pigtail renders the shield useless.
Useless. It might as well not be there.
So what's the right way? How do we connect this shield without twisting it?
A 360-degree connection. You use a high-quality connector where the metal shell clamps onto the cable shield all the way around like a collar.
Like a plumbing fitting.
Yes, and then that metal shell connects to the chassis or the mating connector. Metal to metal, 360 degrees.
No wire.
No wires, no pigtails. The current flows evenly around the circumference.
It's rigorous.
Yeah.
You can't cheat the physics just because twisting wires is easier.
You cannot cheat the physics. And the same goes for filter placement. This is another classic mistake.
Oh, right. Putting the filter on the board. Where does it go?
It depends on your enclosure. If you have a shielded metal box, a Faraday cage, the filter must go through the wall.
Literally through the metal.
Yes. It acts as a bulkhead. Imagine the metal wall as a quarantine zone. The dirty noise is on the wire outside. The clean circuitry is inside.
Okay.
The filter sits right in the wall.
What happens if I bring the wire inside the box and then put the filter on the PCB?
You failed, because now you have the dirty wire inside your clean box.
Oh.
The noise radiates from that few inches of wire, bypasses the filter, and jumps onto your clean circuitry.
It jumps over the fence.
Exactly. We call it stray coupling or crosstalk. You bypassed your own filter.
And if the box is plastic? If we don't have a metal wall? Then the filter goes right at the entry point, the connector. And, this is crucial, you must keep the dirty external cables physically separated from the clean internal circuitry.
Don't tie wrap them together.
Never. I have seen people bundle the input cable dirty and the output cable clean together with a zip tie to make it look neat.
Oh, no.
The noise just couples right from one cable to the other, bypassing the filter entirely.
It's like washing your hands and then immediately shaking hands with someone who has the flu.
Perfect analogy. You just undid all the work.
Separation is key. Distance is your friend.
Indeed.
This has been such a comprehensive look at the physics of EMI. It's dense, but I feel like we've really demystified it.
I hope so.
Let's try to summarize the key takeaways for the listener who is maybe driving to work or sitting in the lab right now wondering why their board is failing.
I think the summary comes down to 4 main points.
Okay.
1, it is not magic, it is physics. Treat it that way, don't guess, diagnose.
2, differential mode is controlled by loop area. Focus on your PCB stack-up, signal next to return, make those loops microscopic.
Get the geometry right.
3, common mode is controlled by impedance. Keep your return planes solid, no cuts, and use filters like chokes to block the ghost currents.
Okay.
And 4, never forget the efficiency difference. Common mode is 1,000,000 times more efficient at radiating than differential mode. A tiny leak sinks the ship.
And don't do pigtails.
And absolutely no pigtails. 360-degree terminations only.
I want to leave the listeners with a final thought. We talked about how twisting a shield into a pigtail, a tiny geometry change, just a twist of wire, can ruin a product.
It connects back to the bigger picture. We often focus on the big processors, the expensive FPGAs, the complex code.
The glamorous parts.
But in EMI, the hero or the villain is often via a spacing, a ground connection, or a screw.
So if a millimeter of wire at a connector can destroy compliance, what other small details in your design are actually the most critical components?
That is the question. We need to look for the hidden antennas in our own designs. That is the challenge.
Huge thanks again to Fresu Electronics and Dario Fresu for providing these incredible insights. The black magic feels a lot less magical and a lot more manageable now.
It was a pleasure.
Check out the show notes for the diagrams we mentioned.
Yeah.
You really want to see that donut radiation pattern to believe it. Until next time, keep those loops small and those return paths solid. Thanks for listening to The Deep Dive.